Hello, my name is Zachary Mansour. I'm an electrical engineering student working on a microplastic filtration system that will be deployed in Presque. Right now, I'm working on 3D printing the final part of the enclosure for the entire electrical system. This will be the lid that's going to be printed. This lid right here is about what it's going to look like. This one's a little bit too large. And this will finalize all of the mechanical requirements for the electrical system in the water filtration system. The electrical system is made up of two main parts, the control system and the power system. The power system starts by inputting a voltage of 24 volts to these two stacked DC to DC converters. The top DC to DC converter is used to convert that 24 volts to 24 volts to give a steady voltage to the DC water pump. Underneath that is a 24 volt to 5 volt DC to DC converter used to power the Arduino Nano microprocessor, which will be used to power all of the other 5 volt components in the system. Moving on from the power, you can see here this is a DC H bridge. This is a 2-channel H bridge. Although we'll only be using 1 channel, this leaves room for future expansion. This H bridge will vary the voltage between 0 and 24 volts to give an ideal flow rate out of the DC water pump. Moving over here, like I said, this is the Arduino Nano microprocessor, which will be used to control all of the data throughout the entire system. And then over here are the 3 sensors. We have a current sensor, a UV light sensor, and a voltage sensor. These will be used to give data feedback on how the system's actually working and at what power cycle it should be involved in. So now I have the electrical system set up to my test bench. Here I have a 12 volt power supply hooked up. Now this isn't the actual voltage that's going to be used, it's going to be a 24 volt power supply, but this still works fine for the test bench to get accurate data. Over here I have a UV light sensor that's just kind of hanging here to give the ambient light reading in the room. This will actually be attached to the solar panel to give the actual UV reading from the sun. And then I have the voltmeter hooked up to the input to the power supply, which will give us an idea of what the power input is going to be. And the current sensor is also wired to this input, but it's going to be reading very low current because there's no pump actually hooked up at this point. The software for this system can be broken down fairly easily by looking at the different functions used to create this program. The first is the current function, which is used to translate the data from the current sensor into a readable current in amps. The motor function is used to create a duty cycle on the H bridge between 0 and 100% that will modify the voltage output to the water pump. The UV function is used to translate the data from the UV sensor into a readable UV index. And the voltage function is used to translate the data from the voltage sensor into a readable voltage in volts. Taking all of these functions together, you can create a simple program that will cycle through different power modes and give data based on what's happening in the surrounding area. By looking at the serial monitor, we can see the serial output from this system. And we can see that right now we're in full power mode with a UV index of 6.02, which is the UV index in the room. A current rating of 0.2, but that's going to be very low because there's no actual motor connected to the system. And a voltage of 12.324 volts, which means that this system is running in full power mode because the voltage is high enough that the system believes that it can keep working at full power without any struggle. On my test bench, by disconnecting the 12 volt power supply, the H bridge and the pump, if it were connected, are now being powered by the internal logic of the microcontroller, which means that the voltage reading is going to be much lower, and we can see that now the system is in power saving mode because the voltage is at 3.947 volts. Because of the low voltage, along with the low current and the low UV index, the system believes that it can't run at full power and must conserve its power until it's able to charge its batteries back. Thank you for watching my video. I hope you enjoyed learning about this project as much as I enjoyed making it. Thank you.